Hello everyone, welcome to Science Spot. This podcast shines a spotlight on the latest scientific technology from Japan. Your host is Ren from Science Talk. Today's topic is the Alzheimer's disease, and most people likely associate with a condition where brain functions, such as memory, gradually deteriorate. One of the major causes of this disease is believed to be a protein called amyloid beta. When this amyloid beta abnormally accumulates in the brain and self-assembles into fibers, a process called fibrillation, and it's thought to be a key to the onset of the disease. You can imagine it like tiny pieces of garbage accumulating in the brain, tangling up and forming large clumps that hinder brain function. However, there are various types of amyloid beta, and particularly for familial Alzheimer's disease, which is a herediitary form, and the detailed structures of many mutant amyloid beta types remained unsolved. So I'm highlighting a particularly fascinating study on the familial mutant amyloid beta called Tottori type. This Tottori type amyloid beta is characterized by a D7N mutation, where the aspartic acid D at the 7th position in amyloid beta's amino acid sequence is replaced by the asparagine N. It was known that this mutant amyloid beta exhibits unusual aggregation behavior. So why has the structural analysis of this Tottori type A beta been so challenging until now? The problem is that when experiments are conducted on Earth, this Tottori type A beta tends not to form an ordered amyloid fibrils. And instead it forms chaotic, irregular masses known as amorphous aggregates. Imagine trying to build a specific shape with building blocks, but instead they always just pile up into a messy heap, making it impossible to discern any clear shape. This makes it incredibly difficult to study its structure in detail. This is where the research team turned their attention to an unexpected space. A research group centered at the Exploratory Research Center on Life and Living Systems used the Kibo, Japanese experiment module on the International Space Station. In space, under microgravity conditions, gravity-induced convection and sedimentation, which occur in Earth, are suppressed. This allowed them to limit the formation of amorphous aggregates and efficiently promote the formation of high-quality targeted fibrils. And to give you an analogy, if you put sugar in water on Earth, gravity causes a denser sugar to sink, and the convection can make it difficult to dissolve uniformly. But in the microgravity environment of space, these forces are largely absent, allowing for more precise control over materials. And thanks to this unique microgravity environment, Tottori type A beta, which was previously impossible to analyze, was able to fibrilize like a perfectly ordered crystal, making detailed structure investigation possible. For the structural analysis, they used a highly advanced microscope called a cryo-electron microscope. This technique allows researchers to observe frozen samples using an electron beam, revealing incredibly tiny structures at the nanometer to atomic level. It's like taking ultra-high resolution photographs of molecular blueprints. The results of this analysis revealed a surprising fact. In the fibril structure of Tottori type A beta, The N-terminal region of the protein was found to be flexible and lacked an order structure. This suggests that the N-terminal core structure stabilization mechanism seen in the wild type or normal A beta is lost in the total type. The D7N mutation is believed to cause changes in charge balance and an increase in hydrophobicity, which in turn promotes amorphous aggregation and hinders proper fibril formation. In essence, this mutation was the reason why A beta couldn't form proper fibers and instead created disordered clamps. This study is the first to structurally demonstrate how a microgravity environment affects the protein aggregation processes. It holds a significant potential for advancing our understanding of Alzheimer's disease's pathology and for developing new structure-based therapeutic drugs. It's truly like something out of science fiction, isn't it? That experiments in space are helping us find keys to protect our health. So that's all for today's Science Put. This podcast is broadcast daily on weekday morning in both Japanese and English. Next week, I'll be temporarily returning to Japan from London, so I might only be able to broadcast on Monday. And I'll share more in Monday's episode, but I recently appeared on the show for Nippon Broadcasting. This is a Japanese radio station. Look out for that, as both a Japanese and English version will be available. I'd love for you to listen to the podcast and post your notes and thoughts with the hashtag SciencePut. See you next time.